Hello everyone. Just let me check if I am live on YouTube as well. Just give me a second and I will be starting the lecture. Just wait a second. I'm just confirming if I am live on YouTube as well and if I can be heard there. Starting the lecture. Just wait a second. Alright. So I think I am audible and visible both on Unacademy and YouTube right now. If you cannot hear me, then try reloading the page because on an academy, if any of you, Apu and Piyush, can confirm that if I am audible and visible, I will be continuing to the editorial of the today's problem, cool subsets, right? So just before we start this lecture, I just want to confirm. I just want to let you all know that this is a live session, so you can ask me doubts at any point in the lecture, and I will be solving those doubts when they are coming in. I will be explaining this problem, the solution to this problem, but I'll also be taking doubts. So any on-topic doubts that you guys have, you can ask me during the lecture at any time, or if you have any off-topic doubts, you can ask me those as well at the end of the lecture. So today we are going to be looking at cool subsets. This was a problem in CodeChef Long Challenge 2021, the January challenge. The problem code is COOLSBST. Let's look at this problem first. I'll try to also uh, make you go along with my thought process as to what I was thinking when I was solving this problem. And yeah, we'll be looking at the final solution as well. So let me share my screen onto my problem. Is the problem visible? Can anybody on the chat confirm if the problem is visible or not? For all of you, the problem code is COOLSBST. The problem link is here. I'll be posting the problem link on the Academy chat. You can see from the description for the YouTube chat. You can check the link from the description. So in this problem, an integer x is cool if it has a primitive root modulo x, right? This first line already imposes upon you a great kind of knowledge that you have to have before you even start to attempt this problem. So an integer x is cool if it has a primitive root modulo x. What is primitive root? What is modulo x? So these are things that you have to know before coming to this contest. But primitive root is basically a generator which generates all the numbers for a modulo n, and there is should be here. Let's never mind. The primitive root modulo x only exists when, let me write this down. The primitive root modulo x, primitive root modulo x only exists when x is either 1, x is either 2, x is either 4, or x is some p to the power k where p is an odd prime, right, where k is greater than 1, and x is some 2 into p to the power k where p is again an odd prime and k is greater than 1, greater than or equal to 1, right? So these are the 5 cases that we are going to be looking at: case 1, case 2, case 3, right, case 4, let me write this down, and case 5. These 5 cases are the cases when we know number has a primitive root modulo x, right? When x is 1, when x is 2, when x is 4, when x is p to the power k, when x is 2 into p to the power k. This knowledge you have to have before, because the proof of this theorem is too long for you to be able to construct during the contest itself, right? And if you want to know more about primitive roots and sort, you can look upon primitive roots online, and the existence of primitive roots, which basically says x has to be either one of these 5 cases for there to be existing a primitive root here, is a theorem that was proved by Gauss in 1801. So with this out of the way, just give a thumbs up if you do understand that when a primitive root modulo x exists, right? Either it is 1, either it is 2, either it is 4, either it is p to the power k, or 2 into p to the power k, where p is an odd prime and k is greater than or equal to 1. You have to have this knowledge before you even start to attempt this problem, right? Then an integer x is cool if it is a primitive root modulo x. We first we get out of this line. You have to have knowledge about this. I learned about this in my college curriculum of number theory. You might learn this through some online course on number theory, like on an academy. But you have to learn this before attempting this problem. Next, we come on to the coolness of a non-empty set of n distinct integers. Let me actually share my screen. Sorry, I forgot to do that. Application window. So the coolness of a non-empty set of n distinct integers, s is equal to x1 to x2 up until xn, is the number of cool divisors of product of I equal to 1 xi up until n, right? So the coolness of a non-empty set of n distinct integers, we have a set of non-empty distinct integers, and the number of cool divisors of product of x1 into x2 into xn up until whatever that product is, the number of cool divisors it has, that is the coolness of this set. We define it like this, right? Now the actual problem is you are given 4 integers L, R, A and B. Let S be the set containing all integers between L and R inclusive. So S is the set containing all integers from L to R, that is L, L plus 1, L plus 2 up until R. Consider all non-empty subsets of S with sizes between A and B. So we have to go through every subset of S that is between size A and B, right? We are going to be looking at an example, but we have to basically go through every subset of S and look if the size is between A and B. Find the sum of values of coolness of all these subsets. Whatever these subsets are, we have to find the sum of the coolness of these subsets. Since this sub can be large, computed modulo 998244353, the input is given t test cases, and in this t cases we are given L, R, A and B. T is 10 to the power 5, LR is 10 to the power 5, AB is 10 to the power 5. We are given a subtask 1 where R is less than or equal to 16 and B is less than or equal to 16. This basically means you have to naively, brute forcefully compute the solution, right? Subtask 2, there is given A is equal to B. This is basically a hint that you should first try to cover the case when A is equal to B, and then you should go to the case where A is not equal to B, and we have to find the sum of the coolness from A to B, right? So we are given an example input and the example output. Let us look at this example input and the example output, right? So 3, 3, 4, 1, 2. Let us look at that one first. So we have the first test case 3, 4, 1, 2. Here 3 and 4 are the L and R values, L and R, and these are the A and B values, right? This basically means we have the set 3, 4, right? Seeing all the non-empty subsets of 3, 4, we get the first subset to be 3, the second subset to be 4, and the third subset to be 3, 4. All of these subsets have sizes between 1 and 2. This A and B are given to be the sizes of the subsets. So all of these subsets have sizes between 1 and 2, right? Here we want to calculate the coolness of these subsets and take their sum, right? So here the coolness of the subset, to calculate the coolness of this subset, we have to take the product of all the elements in there. So the product is 3 here, the product is 4 here, the product is 12 here. The divisors of 3 are 1 and 3, the divisors of 4 are 1, 2 and 4, and the divisors of 12 are 1, 2, 3, 4, 6 and 12. Now how many of these numbers have primitive roots? 1 has a primitive root, as we have seen. This is according to case 1. 3 has a primitive root. This is according to the case 4 we have explained before. Here 1 has a primitive root, 2 has a primitive root, 4 has a primitive root. Here as well, 1, 2, 3, 4, 6. Up until here we have primitive roots, but 12 won't have a primitive root. This is not a cool number, right? Because this does not fit in any of our cases, right? This is basically 4 into 3, so this does not fit into any of our cases, but all of these other numbers fit into our cases. This is according to case 5, 2 into 3, right? So 2 into 3 to the power 1. So this also fit in one of our cases. All of these fit into one or the other case, but 12 doesn't fit in there. So the sum of coolness is basically 2 plus 3 plus 5, which gives us 10. As the sample output was 10, this is the correct answer, right? Let's change the example problem a bit. Let's say instead of A being given as 1 and B as being given as 2, we were given 2 comma 2. Then we couldn't take these subsets. We only have to take this subset, and the answer would have been 5, right? Just give a thumbs up if you do understand up until here completely on the Unacademy chat, and also just write yes on the YouTube chat if you do understand the problem completely now. And then I will be going forward to explain how we can try to solve this problem. So Mihir Samant asked, are advanced concepts of trigo needed for CP? No, you do not need those. I mean, if you are going for advanced CP, you might need those. There might be a rare 1-2 questions on advanced trigonometry, but generally you do not require that. And I liked how I noticed this in the Wikipedia article that was attached to the link. Yeah, the existent criteria is also attached in the Wikipedia article. I was not able to find that right now, but yeah, it is also attached in the Wikipedia article. This is a really well-known existence property, so it should be treated as common knowledge, right? That these 5 cases are the things where primitive root exists. Next, we come on to subtask 1, right? In the subtask 1, R was given less than equal to 16 and B was given less than equal to 16. As I said, this is a subtask where you have to brute force your way, right? You can brute force your way in trying to create all of the subsets it would have. So L minus R would have maximum of L minus R plus 12 would be a maximum of 16. So there would be a total of 16 elements in this set. Taking all of the subsets of it, you would have 2 to the power 16 subsets, right? Also, if A is equal to 1 and B is equal to 16, you can have all of these subsets, right? Trying to calculate the product of all of those. You calculate the product and then you find out the primitive root. The time complexity would be around big O of T into 2 to the power 16. Somewhere around that. You might apply a log for other functions as well, but that would be something polynomial. The time complexity would be somewhere along this, and in this time complexity, I think you can complete the subtask 1 of the solution. The question is, how do we improve from this brute force approach? So in the subtask 2, you should try to do the problem subtask by subtask in CodeChef Long challenges. In the subtask 2, we are given that A is equal to B. Let's try to find out what would happen for A is equal to B. Basically, we are given some L plus 1 up until R integers. We want to create all the subsets of set S. Let this set be S of size A is equal to B, which is given in our input, right? Of size A equal to B. And then when we create all of those subsets, we would have we would take the product of all of the numbers in that subset. So if we have a subset, like say S dash is equal to some A1 comma A2 up until AA, we would take their product, AI product, that would be some number P, and we want to see all of the divisors of P and see if those are cool or not, right? So instead of doing all this, the final formula that we are writing for our answer would look like something like this, which is uh, sum of all these sets, right? We have the set S. We have the set S first, which comprises of numbers from L to R. We want to take all of the sets such as C, which are a subset of S, and size of C is equal to A, capital A given in the input. We want to find out the product of all of these numbers, right? The product of all of these numbers, which is X in C. When we find out the product here, we want to see if its divisors are cool or not, how many divisors of its are cool, right? So instead of doing it like this, what we are instead going to do, we are going to do if our primitive root of this sort, if one of our cases, right, is a factor of the product or not, right? So we are going to be looking case by case and trying to see if one is going to be a factor of whatever product we get in that subset. We are going to see if 2 is a factor of whatever product we get in that subset. Is 4 a product factor of whatever product we get in the subset? If p to the power k is a factor, and if 2 into p to the power k is a factor, right? And then we sum those up. So instead of going to each number and seeing if its divisors are cool, we're going to each cool number and seeing if it's a factor of the product, right? So first we'll go to the case 1, right? And how many subsets exist where 1 is a factor of the subset product. This is easy. How many subsets exist of size B, right? Of size B, A is equal to B. And between L and R, how many such subsets exist? The answer is easy. It's just R minus L plus 1 factorial by B factorial into R minus L plus 1 minus B factorial, right? This is the answer. It is basically the size of the set S. This is the size of the set S. This is the size of the set C. We can choose a set in this. We can choose a subset in the entire set of size B by this many values, right? And this is nothing but R minus L plus 1. Choose B, right? In this many ways, we can choose a subset in this entire set, and in each subset we would have a factor 1, right? So for case 1, the number of value that is going to be added in our answer is R minus L plus 1. R minus L plus 1. Choose B. Just give a thumbs up if you do understand everything up until here, that this is going to be a constituent in our answer according to case 1. We are looking at subtask 2 right now, where A is equal to B. Right? Also in the Unacademy chat, YouTube chat, you can give a yes if you do understand up until here, that according to case 1, we are going to be adding R minus L plus 1, choose B, into our answer. Next, for case 2, we have to find out how many such subsets exist which has a factor of 2, right? Which how many such subsets exist such that this subset product has a factor of 2. And here we have to look at, here we can instead do what we are going to do, subsets with factor 2. This case 2 is basically x is equal to 2, right? Subsets with factor 2 is equal to subsets, total number of subsets, total number of subsets minus number of subsets which don't have a factor of 2. Is this understandable to all? To find out the number of subsets which when multiplied against each other has a factor of 2, we are just going to be using inclusion exclusion to find out. Just take the total number of subsets, subtract the number of subsets which don't have a factor of 2, and we will get the number of subsets which has a factor of 2, right? And according to this, the number of subsets which don't have a factor of 2 are just the number of subsets we can make with odd numbers, right? When we multiply odd numbers with odd numbers, we would get a final odd number as a resultant. If there is even a single even number in that whole product, then we would get a even number, right? So we are going to be using this to find out. Just give me a second. This is going to be of the form r minus l plus 1 by b, which we found out before, the number of total subsets, r minus l plus 1 choose b, minus the number of subsets which don't have a factor of 2 is some odd count by b, right? The number of odd numbers, choose b, right? And the number of odd numbers here, number of odd numbers is equal to r minus r by 2, r minus r by 2 floor minus l minus 1 minus l minus 1 by 2 floor. You can try to verify this equation. When we have a range from L to R, the number of odd numbers that are in this range is basically R minus R by 2 floor minus L minus 1 minus L minus 1 by 2 floor, right? So this is the constituent according to case 2 that we are going to be adding in our answer, which is R minus L plus 1 choose B minus number of odd numbers choose B, right? Next we are going to be looking at case 3, which is when x is equal to 4, right? So how many subsets exist which have a factor of 4? We're going to be calculating this just how we calculated case number 2. We're going to be using inclusion exclusion, right? So number of subsets with factor 4 is equal to number of subsets with factor 2 minus number of subsets. Just wait a second. Minus number of subsets which are divisible by 2 but not by 4. Do you all understand this recurrence? Number of subsets with factor which contain a factor of 4 is just the number of subsets with factor 2 subtracted by the number of subsets which are divisible by 2 but not by 4. How do we calculate this value? You might be thinking, right? So we calculate this value by just making sure, right, that to calculate this value, which is the number of subsets which are divisible by 2 but not by 4, we can calculate this by the number of that we have one even number in here, something like 6, which is divisible by 2 but not by 4, and rest are the odd numbers, right? So 3 into 5 into 7 into something 6 into 9 into 11. Rest are odd numbers, right? So there is one number which is divisible by 2 but not by 4, and the rest of the numbers are odd. So the number of combinations which we have is number of numbers which are divisible by 2, not by 4, into the number of numbers which are odd, number of odd numbers basically, right? Number of odd numbers, choose b minus 1. This is this value that we talked about here. And this value we have already calculated in the previous case, right? Let's call that answer 2. Let's say this is answer 2. Let's say this is answer 1. Then answer 3 is just answer 2 minus number of numbers, basically numbers divisible by 2 but not by 4, into odd count, odd numbers, choose b minus 1, right? Because we can select among all of the odd numbers, right? We can select b minus 1 numbers because the size of the subset should be b. So we are selecting b minus 1 numbers as odd, and we are selecting one number which is divisible by 2 but not by 4. So we would get exactly this value, and using inclusion we would get the number of subsets which have a factor of 4. Up until now we have calculated 3 cases. If you do have any doubts in these 3 cases, you can ask me now. Let me look at the YouTube chat as well. It's so boring. Make some interesting, sir. I'll try to make it interesting for you, I guess. But this is basically math, a lot of math work, and you have to go through this math work in order to reach the answer, right? You cannot just skip this math work. And if you are able to follow along with all of this math work, that is great. But there might be people who are not able to follow through with this math work. So if you guys do have any doubts, just let me know. Let me speed through the case 4 and 5, right? Let me take some time on case 4, and then I would go to case 5. I will speed through case 5 because that is really similar to case 4, right? Once we have covered those 2 cases, then I will get to the last subtask, which is a subtask 3, which would require square root composition. So look forward to that. That is really interesting, right? So the case 4 is x is some p to the power k, where p is some odd number, some odd prime number, right? And here we are not going to be doing what we did in case 1, case 2, or case 4. Here there is going to be a little change, right? When we have some b numbers, let's say a1, a2 up until b in a subset, and we take their product, which is product of ai, right? How much a1 how much a1 basically, sorry, just give me a second. How much will a1 contribute to the case 4 answer, right? So a1, let's say the factorization of a1 is some 2 to the power t1 into p1 to the power t2 into p2 to the power t3. It has a factorization like that, right? So when we calculate the final product, this product will have p1 t1 into whatever the values of p1 are in there, right? So p1 t1 plus whatever a2's p1 value is p1 to the power t4, right? So t1 plus t4. ab has p1 to the power t5, so plus t5 here, right? So the P1 value here would have the sum of the products of its constituent values. So A1 will contribute T1 values to the case 4 answer, right? Because we can take here P1 to the power 1, P1 to the power 2 up until P1 to the power T1 corresponding to A1. Now if we want to see how much A2 contributes the values P1 T1 plus 1, P1 T1 plus 2 up until P1 T1 plus T4, right? It contributes T4 values to the number of cool divisors of this product, right? So each number contributes the number of powers of its prime number to the product here and to the number of cool divisors of this product here, right? So we can pre-calculate the sum of the factorization here. Basically what I'm trying to say, if a number n has the factorization to the power some we don't care about this, to the power c, let's say, into P1 to the power T1 into P2 to the power T2, all of these would be odd primes first of all, right? Pk to the power Tk. Then we would calculate Fn, which is just T1 plus T2 up until Tk. We would calculate this for every number from L to R, right? We will calculate this for every number from L to R, right? And we would sum these up. We can sum this up, and the final answer that contributes according to case 4 in the final answer is just sum of Fi's, right? Sum of Fi for I is equal to L to R. This is the final value that is contributed to an answer according to case 4. Summation of I is equal to L to R Fi into R minus L, choose B minus 1. Right? Because if we select A1 in our subset, then we can select all of the other numbers, choose B minus 1, right? We can select all of the other numbers, if we select A1 here, then we have B minus 1 choices here and R minus L choices to fill them from. So we would have R minus L, B minus 1 choices in the right hand side and the sum of Fi's in the left hand side. This is the answer that contributes to the fourth test case. And because this is going a little bit more mathy, I'm going to be mentioning what the case 5 is. The case 5 is being calculated similar to how we calculated the case 2 one, and you can calculate this according to, let me just write down the final result for case 5. You can try to work out why this would be the final value that would be contributed to our answer. Case 5, the answer 5 is just summation of I is equal to L to R Fi into R minus L, choose B minus 1. This is what we calculated before. We will use inclusion exclusion to subtract. Case 5 is the one where x is equal to 2 into p to the power k. Just so that you know. We would subtract from here summation of I is equal to L to R Fi, and another imposition, another condition on I here, I is odd, right? So the odd numbers which come from L to R, we sum those Fi's up and multiply this with the number of odd numbers, choose B minus 1. So this is the final value that is contributed to our answer according to case 5, right? When we sum answer 5 plus answer 4 plus answer 3 plus answer 2 plus answer 1, that would give us our final answer value that we have to output in this question. So these are the 5 cases that we have to look at, and we have to find these values for each of the cases, and finally we have to output for subtask 2. Up until we have looked at subtask 2, what would be the answer, right? So is there any doubt in how we calculate subtask 2? It is just really mathy and really extensive, right? You can do this on your own. You do not have to worry about not doing this on your own. You just need a lot of time. As in long challenges, you get a lot of time. You have 10 days to find out the answer, right? So trying to find out what would be the answer for each case, you just need a lot of time and have to write everything down that you are thinking. And finally, you would get on these values, and subtask 2 would be completed here, right? Then for subtask 3, which is the final thing, here we deviate from maths. We don't require any math here. We actually require some math here, but here we get onto the thing as to how we efficiently compute these values to sum from A to B, right? Basically now A is not equal to B, and we have some range. A is less than equal to B is less than equal to 10 to the power 5, right? And we have to find these values, these cases values for each B in among these, and we have to sum those up. How do we sum those up, right? If we look back at the answers of all of these test cases, let's look back, right? The case 1 values depends on B, right? In this kind of equation, R minus L plus 1, choose B. So it depends on B, but it only depends on B in this kind of equation where we have to sum up, where basically we have to sum up here. Let me write this down here. So we have to sum up x is equal to A to B, R minus L plus 1, choose x, right? We have to sum this up here, right? So we can sum this up by finding out R minus L plus 1 x summation x is equal to 0 to B minus sum of x is equal to 0 to A minus 1 R minus L plus 1, choose x, right? This value is exactly equal to this value, right? We're just taking the prefix differences here. So if we can find out x is equal to 0 to sum to B R minus L plus 1, choose x, then we would be able to calculate this. Then we would be able to calculate the answer value which is contributed into the final answer according to case 1, right? So the whichever value is contributed in our answer according to case 1, we can find it out. If we can find out x is equal to 0 to B R minus L plus 1, choose x, right? In case 2 as well, the final answer was this, which we have already computed before, and the second answer is this. Here as well, we want to find out, let me write this in a new slide. So we have number of odd numbers, but this is between L to R, right? This is between L to R. This doesn't depend on B at all. Choose B. We have choose B down below, right? So instead of that, let us write choose x here, and we want to sum from x is equal to A to B. This can again be written as we have written in case 1. We will just be writing number of odd numbers, choose x, sum x is equal to 0 to B, minus sum x is equal to 0 to A, number of odd numbers, right? Choose x. This is a really simple trick, but I just want to make sure that you do understand what we're trying to do here, right? Again, we come to case 3. In here as well, the final answer, which is answer 3, is equal to answer 2 minus number divisible by 2 but not by 4. This depends on L to R. This doesn't depend on B. Answer 2 we have already calculated. This again depends on only on the B value, which is below here, right? This can also be broken down into odd number x summation of I equal to 0 to B minus 1 minus summation of I equal to 0 to A minus 2 odd number x, right? So subtracting these two, we would get this value according to case 3. For case 4, it would be similar. There is R minus L B minus 1. We can break those down into two values. this is I is equal to L2 R Fi, right? That depends on L and R. It doesn't depend on B at all. And here as well, the answer only depends on this. We have already computed this. We only want this value. So finally, what I want to tell you about is in subtask 3, we only want to from subtask 2 to subtask 3. Just wait a second. From subtask 2 to subtask 3, we only have to compute. We only have to compute summation of I equal to 0 to k and choose I efficiently. Right? If we can compute n choose I summation of I equal to 0 to k efficiently, then we can basically do our subtask 3. We just have to compute this value efficiently, right? If we can compute this value efficiently, we would be able to transform from subtask 2 to subtask 3, and we would finally get a final answer, right? So how do we compute these values, and what kind of process we'll be doing to compute these values? So here we would require square root decomposition, right? Basically, just give me a minute. We would be let us number this. Let us put this function as some s, right? Sn comma k is nothing but summation of r is equal to 0 to k and choose r, right? Let's make this as n comma k, right? What would be the range of n here? The range of n can be anything from 1 to 10 to the power 5, right? And k can also be anything from 1 to 10 to the power 5 as given in the input, right? So we want to compute, if we are given some n comma k query, we want to compute Sn comma k efficiently. We just want to do that. So to do that, what we are instead going to do in square root decomposition, we're going to be calculating the Sn comma k for some specific n's beforehand. Basically, let's make this whole matrix. Here it's going to store s1 comma 1. Here it's going to store s1 comma 2 up until s1 comma 10 to the power 5, something like that. It doesn't make sense, but let's just suppose it does store that. Here it would store s10 to the power 5, choose 1. Here it would store s10 to the power 5, choose 5. If we computed this whole matrix, if we decide to compute this whole matrix, of course it would take 10 to the power 5 into 10 to the power 5 time, which would TLE, because it would take 10 to the power 10 operations. But instead what we are going to do, we are going to calculate some rows here. Let's say we calculate the first row. Then we calculate some, let's say we calculate the first row. Then we calculate the one plus some block size row, right? Let us name that by small b. Here small b means block size. Then we would calculate some 1 plus 2b row, and we would calculate the 1 plus some nb row, right? Not nb, let's name that as some kb row, right? We would basically generate some b blocks here. We would basically pre-compute some rows here, right? And we can compute these rows very efficiently because we know that s n comma k is nothing but summation of I equal to 0 to k and choose I, right? And this is just equal to summation of I equal to 0 to k minus 1 and choose I plus n choose k, right? So that basically means s n comma k is nothing but s n comma k minus 1 plus n choose k, right? So we can just iterate s1 comma 2 would just depend on s1 comma 1, S1 comma 3 would just depend on S1 comma 2, S1 comma 4 would just depend on S1 comma 3, and like this we can compute up until here. S1 into 10 to the power 5 would depend on S1 comma 9999, and we can compute these rows very efficiently. How much time complexity would we require to compute these rows? Let the number of rows be n by b, right? The number of rows, let that be n by b. We are going to be spending n by b into n time to calculate these rows, right? B is the block size, n is equal to 10 to the power 5, right? And b is the block size here. So we are utilizing big O of n by b into n time to pre-calculate these rows. Now, when we want some Sn comma k, let us, we are given Sn comma k here. We want to look at these rows and find the answer efficiently. If this n is among one of these rows that we have already chosen, we have the answer. We have already pre-computed this answer, and we can just look at those rows and find the answer that we want, right? What if the n that we choose is not in our block chosen, right? Let's say the Sn comma k lies somewhere here. Then we want to compute this Sn comma k from either here. We want to traverse in this direction. This where each iteration takes some constant time, right? Some small time. Then we can go like here, or we can go like here, or maybe go like here. I'm not sure. We just want to be able to reach Sn comma k in some small number of steps, right? From the already pre-computed rows, right? If we can reach Sn comma k from already the pre-computed rows in some small unit of time, then we can finally, let's say the number of steps we take to get to Sn comma k from some pre-computed row is at max b, right? We require b iterations to reach Sn comma k, and the amount of time it requires to iterate one step is constant. So we would have another time complexity of big O of q into b, right? Q is the number of queries we have, which is around n, right? This is around n, because we have a test cases of 10 to the power 5, and in each test case we are doing this operation 5 times or 6 times or 7 times, right? So q is around n, and this would be the time complexity of trying to find out the Sn comma k value from this pre-computed rows values, right? Is it clear up until now? Just write it in the YouTube chat, yes, if you can understand, if it is clear up until now. We just want a way that we can iterate from one value to one pre-computed row to some Sn comma k, where we can go down the nth value or go up the nth value by some method, right? And that some method again comes into mathematics, right? We have Sn comma k is equal to Sn k minus 1 plus nk. We also know that n choose k is equal to n minus 1 choose k plus n minus 1 choose k minus 1, right? This is a well-known property of binomial coefficients. You might have learned this in school. Basically, n ck is equal to n minus 1 ck plus n minus 1 choose k minus 1, right? So this is a well-known property, and I'm going to be using this to calculate some kind of iteration method that we can apply on this table, right? So here what we are going to do is sum this up for r is equal to 0 to r is equal to 1 to k, right? We do not want k to be negative. We are only going to be having it as positive, right? Or we can have it negative as well. Actually, it doesn't really matter. So for r is equal to 0 to k, we're going to be summing up n r is equal to summing up of r is equal to 0 to k, n minus 1 choose r, plus summing of r is equal to 0 to k, n minus 1 choose r minus 1, right? Then that means we have s n comma k is equal to s n minus 1 choose k plus s n minus 1 choose k minus 1, right? And that basically means we also have the previous equation, which is Sn comma k is equal to Sn k minus 1 plus n choose k, right? So putting that in here, actually, how do I put that in here? Just give me a second. Yes, combining these two equations together, right? Sn choose k is equal to Sn minus 1 choose k, Sn minus 1 choose k minus 1, and this equation, we get the final equation, which is Sn choose k is equal to 2 times Sn minus 1 choose k minus 1 plus n minus 1 choose k. Yeah. So this is our final equation which we are going to be using. And in here you can see if we have some value Sn comma k here, from that we can calculate Sn plus 1 comma k plus 1, right? From that we can calculate Sn plus 2 comma k plus 2 really efficiently as well in constant time. And like this we can go to Sn plus t comma k plus t, right? So we have already pre-computed this nth row. From that we can calculate the n plus tth value in block size value, right? So the total time complexity here is big O of nb into n plus big O of q into b, right? So big O of n square by b plus qb. If you try to find out what the optimal b value here would be, it would be around big O of root n. So taking big O of root n, we would get big O of n root n plus q root n, which would be big O of n plus q root n, or basically n root n, right? So all of our the problem would be done in n root n time complexity. So the problem is now complete. First we have to look at the subtask 2 and calculate the values at each of these five test cases, and finally use this square root of decomposition method to pre-compute some rows and use those pre-computed rows to find out the values of the next values, right? So let me share a code. This code is not mine. This is a code of Radoslav Medetro. So let me share my screen onto my code editor. Share screen onto my code editor. I have shared it on Unacademy. Let me just share it on YouTube as well. So let me put another window capture here. Create new. It would be sharing the Visual Studio Code. So can you see my code editor? I'm most probably sure that you can see it right now. Yeah, you can see it, right? So in this code, Radoslav, what basically he does, he takes an e, he pre-computes. The pre-compute function is really important here, right? In pre-compute, what he does, he takes the block size. He have already put the block size as 250, which is around square root of 10 to the power 5. He has fine-tuned it to be the exact value at which the code runs in the fastest time, but it would be around 250, right? In here, I is equal to k by b. He's basically creating the rows in the diagonal fashion. I have created the rows in the horizontal fashion. I have created the rows in the horizontal fashion, and then I am going from the horizontal rows to any value in a diagonal fashion, right? What he has done, he has created the rows in the diagonal fashion, and when he wants to find out any Sn comma k, he is going in the horizontal fashion and finding out that Sn comma k value, right? So he would be he's pre-computing I comma 0 as 1 and pre-computing I comma n as 2 times I n minus 1 minus cn minus choose k, right? So this is basically his pre-computing function where he's pre-computing these rows. This fixed function is just him taking modulo. Do not worry about that. So when he pre-computes these values and also does other stuff which is required for the first 5 test cases, right? To calculate those first 5 test cases, you require count odd, count 2, many other stuff. So he also pre-computes that so that he can efficiently take prefix sums there, prefix differences. Then he reads the values and then solves. In solves, he's basically doing solve LRB minus LRA minus 1. This would work, of course. So here he's doing for L to R, and the B value is the number of subsets we want, which is K. He's taking all of the 5 values, and in all of these 5 values, whenever he require function which is R minus L plus 1 choose K, right? We require this value as seen. So he's using the comsum function to calculate Sn comma K, right? We required R minus L plus 1 K S R minus L plus 1 choose K, right? So he's using the comsum function for that, and the comsum function basically uses the previous pre-processed rows to calculate whatever value you want. He's adding Cn comma St for each iteration, right? So he's going into the horizontal fashion, and he has pre-computed in the diagonal fashion. It would be similar to how I did it. I did it by pre-computing in the horizontal fashion and going down in the diagonal fashion, right? So these two are really similar, and he has chosen in this way, and he finally has just outputted his answer. So this is the flow of this code. You can look at this code in more detail to try to find out what you want to find out and how to do this, right? So you can do this by looking at the editorial of this problem. In the editorial of this problem, this is as the tester's solution, so you can go and look that if you are interested about that. So yeah, this was the video editorial for cool subsets of the January Long Challenge 2021. I hope you enjoyed this, and yeah, I will be ending the session here, and looking forward to in the lunchtime contest. The lunchtime contest comes next, so do participate in that as well.